Good morning, student. Today I have to teach about the refraction. I told you that we will consider the topic that's called refraction. How the refraction is taken place. This is an interface that separates the two media. This is interface AB. This is medium 1, that's called rarer medium, and this is called denser medium. And here, this is a ray that's entering into the strike on the interface. And if I draw a normal on the interface, this angle is called angle of incidence, and this ray that's I denote AB is called incident ray. And the ray that's when it goes from one medium to another medium, it will bend from its path. So this is called angle of refraction, and this ray is called the refracted ray. This ray is called refracted ray. So otherwise it has to go straight in this way, but it will go in this direction along BC. So it will bend from its path by an angle. This angle is called angle of deviation. By this angle it will deviate from its path. So this was called as an angle of deviation. So this is an incident ray, this is a refracted ray, and this N1, N2 is the normal. So when a ray goes from rarer to denser, this is called rarer to denser. It will bend towards the normal. But when it go from, this is I am taking the denser medium. This is I am considering the denser medium. Now this is the normal, then it will bend away from the normal. This is now refracted angle, this is the incident angle. So if the ray goes from denser to rarer, then it is bending away from the normal. But if it goes from rarer to denser, so it is bending towards the normal. Third point I have to consider, if the ray goes straight, this is perpendicular to it, interface, then this angle of incidence is 0 and angle of refraction is also 0. So in that case, ray will not bend from its path. It will not bend from its path. It will bend from its path only when it is going obliquely, maybe from rarer to denser, or from denser to rarer. Well, so three phenomena are occurring, and another phenomena we are saying in this case that there are two laws of refraction. Two laws are, number one, first. This was I am denoting, this is the incident ray and this is refracted ray, and this was normal, this is incident angle, this is refracted angle, this ray is, this AB is incident ray and BC is refracted ray, this N1 and N2 is normal. If you see, in this case, the normal, incident plane, incident ray and refracted ray all are in same plane, number one. Number two, in this case, sine angle of incidence upon sine angle of refraction is equal to refractive index, that's constant. this value is constant, the refractive index. This is refractive index of medium 2, this is 2, this is 1. This is refractive index of medium 2 upon 1. That is denoted as refractive index of 2 with respect to 1. So this value is constant. So these are the two laws that's given by Snell. He was an astronomer, so he gave two laws for that refraction to be taken place. So another phenomena in case of refraction is we can show the principle of reversibility. How the principle of reversibility is working in this case? For example, I have shown that this is the interface, and this ray of light was incident ray, and this was normal, and this is a refracted ray. I placed normal to the refracted ray. This plane mirror is placed on the surface. Plane mirror is placed normal to this refracted ray. This ray, when it is placed normal to this refracted ray, this ray retraces back its path. When we place plane mirror normally to the refracted ray, it retraces back its path. So this is known as reversibility. If I show you how we denote it, for example, we are having, this is the one of the phenomena that's this was array A, B and C, and this N1, N2 was in normal. When ray goes from A to B and B to C, sine angle of incidence upon sine angle of refraction is refractive index of 2 with respect to 1. Now, if I say that ray go from C to B and B to A, then sine R upon sine I is mu 1 with respect to 2. So this was number 1, this is number 2. Because when it goes from here to here, then its refractive index of this with respect to this. When it comes from this to this, then refractive index of this with respect to this. Because here, in this case, when I multiply 1 and 2, so I multiply 1 with 2. So when I multiply 1 with respect to 2, sine I upon sine R upon sine I is effective index of 2 with respect to 1 and 1 with respect to 2. So this cancel out. So refractive index of 2 with respect to 1 is equal to 1 upon 1 with respect to 2. So this means it follows the principle of reversibility. If we reverses the refractive index, then it comes to be refractive index of another medium with respect to first, or first medium with respect to the second. And then another phenomena in this case is, if we look at, this was an interface, and this is the ray of light that's coming, that's striking on the surface, and this was a refracted ray. And this incident ray, this was AB, and BC is the refracted ray, and this mu1 is the refractive index in medium 1 and mu2 is the refractive index in medium 2. And this is the incident angle and this is refracted angle. If I say this sine I into refractive index of that medium, sine r into refractive index of that medium. So sine I upon sine r is refractive index of 2 with respect to 1. So you can write down refractive index of 2 with respect to 1 is equal to sine I upon sine r. Similarly, here in this case is velocity of light in this rarer medium is c and velocity of light in denser medium is v. So we can denote velocity of light into refractive index and velocity of light in that medium into refractive index. So c upon v comes to be mu2 upon mu1. So this is the velocity of light in rarer medium to the denser medium. So this is called refractive index of 2 with respect to 1. Another is if the ray is going from the rarer to denser, its velocity changes, but frequency of light will not change. Frequency remain constant. Frequency never changes when a ray of light goes from one medium to another medium. In this case, this was an interface. If I am denoting, this is the incident ray, this is the normal, this is the refracted ray. So according to law, that's a light equation, c is equal to nu lambda. So if velocity changes, then wavelength also changes, because this frequency does not change. It does not change. Change is only taken place in velocity. With respect to velocity, the wavelength must be changing. So when the ray is entering from one medium to another medium, it's two phenomena, maybe velocity, maybe wavelength, that's changing. So that c is equal to nu into lambda, that's equal to mu2. So v is equal to nu into lambda 1, that's mu1. So you can write down it as a c upon v into lambda upon lambda 1 is equal to mu2 upon mu1. So this can also be the formula. So these are the formulas which we are drawing from it. And another phenomena is the lateral displacement. How the lateral displacement is taken place. So now I will talk about the lateral displacement. Lateral displacement is, this is an interface, again I am taking, this is an incident ray that's striking on the surface, and this is a normal, and this is a ray that's bending. This we have taken, now I am considering this is a glass slab. It's A, B, C and D is a glass slab, and it's striking on the surface, and this is another normal I have drawn. This is the refracted ray from the another surface, and this was normal N1, that's N2, and this is normal N3 and 4, second normal, and this was incident angle, and this is, I am saying P, this is Q, this is R, this is S, and in this case, and this angle is refracted angle. Two normals are parallel to each other, so this angle will also be the R angle, equal to R angle, and ray after passing through the slab, it means bent away from the normal. This angle is called emulsion angle, and when I draw it forward, if you see these two rays, they are parallel to each other, so this means they displace laterally. So if I draw a perpendicular from here, this comes to be the normal. So this distance, this I am taking it to be the m, this distance Rm is the lateral displacement distance. So this we have to find out. By how much distance it's laterally displaced. So how I can consider this ray is going, if it is going in this way, and this total angle is I. So this comes to be I minus R. If I'm taking the triangle Q and 2 and R. Q and 2 and R, if you see, this is a base in triangle. If I took a triangle, this is a triangle, this is a triangle, this is angle theta, this is a base, this is perpendicular, this is hypotenuse. Always base upon hypotenuse is cos angle and perpendicular upon hypotenuse is sine angle. So if I am considering according to it, so this angle is this Q and 2 upon QR is cos R. And now I am taking the triangle Q R M sine I minus R. Always angle perfect, this opposite is perpendicular. This RM is perpendicular. So this is perpendicular upon this hypotenuse. QR is sine angle. So from here, now I will take the means QR from both the equations. From equation number 1, QR upon Q and 2 is equal to, this is QR upon, QR is equal to Q and 2 upon cos R. This is number 1 from this equation number 1. This I have taken on this side, this I have taken on this side. Now I will take from equation number 2. This is equation number 2. So this equation number 2, QR is equal to Rm upon sine I minus R. This equation from 1 and 2 you can equate, both the things are same, so you can equate both the equations. So when you are equating both the equations, Q and 2 upon cos R is Rm upon sine I minus R. So Rm we have to find out, that's the lateral displacement. So when we have to find out the Rm, that's denoted as D, lateral displacement, I put the value of D here. So D comes to be Q and 2. This is the Q and 2. This is, we are saying, the thickness of a slab. So this is denoted as D. So Q and 2 is equal to D. So sine I minus R can be multiplied on this side upon cos R. So lateral displacement comes to be D into sine I minus R upon cos R. So this is the another formula for lateral displacement. Now third phenomena which we have to do, the relationship between the real duct and apparent ducts. So what's that one? This I am denoting, this is I have taken the vessel, and here is a medium. I have taken the water in it. Suppose an object is placed at the bottom. Any ray goes straight. It will not bend from its path, it will go normally, so it's not bending. Another ray goes obliquely taking the incident angle and this I'm taking the refracted angle. If I draw it backward, then it seems to be meeting at this point. So this is the image formed when you see the viewer is seeing this an object, the image seems to be here. So this object seems to be raised by this distance. It seems to be raised by this distance. So actual depth is called, the means actual height, and this is called the apparent height. So we have to write the formula for it also. So how we can write? So this is, I'm saying this is a ray. This is N1. That's this is A. This is B, and this is O, and this is, I'm taking the I, and this is suppose R, and this is N2 and 3. Now, if I took the triangle, another triangle, that's A, O, I. Here, these are N1, N2, N3, and N1A are parallel. And third, this is ray is cutting it. So this angle is I. So this angle also comes to be I. So if I took this triangle AOI, this angle is I. So this is the perpendicular. So IO upon AI is, this is called sine. Now another, this ray, this is crossing edge, this is R, so this is also R. Now I took the triangle BOI. So IO upon BI is sine R. So here this is a denser one and this was rarer. So refractive index is, from here you can denote this I point is very near to O. So BI can be equal to BO. BI can be equal to BO and AI can be equal to AO because I is near to O. So if I write down, instead of AI it's AO and BI is BO, what I do, now in this case, I divide this one sine I upon sine R is IO upon AO, IO upon BO, sine I upon sine R is BO upon AO. BO is apparent height, and AO is real height, and this sine I upon R is Y upon R is refractive index of 1 with respect to 2. So if I am writing here, in this case, refractive index of 1 with respect to 2 is apparent height upon real height. So it is apparent upon real. So I have to make it refractive index of 2 with respect to 1. So it becomes actual height upon apparent height. So refractive index is equal to actual height upon this. So by how much distance it has been raised? So if I have to calculate this distance, the raised distance raised distance only, then what should I do? Then I have to subtract, that's h actual minus h apparent. This was apparent, this was actual. I subtract this apparent from actual, then this distance comes to be. So this is the raised distance. So this is a raised distance. So actual is, that comes to be actual is h apparent into u2 with respect to 1 minus h apparent. So h apparent into u minus 1 is raised distance. Sorry, I have done certain mistake over here. So it was, that's h actual is h apparent upon refractive index of 2 with respect to 1. And refractive index of 2 is itself. So actually h actual minus h apparent is the distance raised. So actual is h apparent into refractive index of 2 with respect to 1 minus h apparent. So h apparent into refractive index of 2 with respect to 1 minus 1 is the raised distance. So this will be the another topic. So thanks. Have a nice day.